the other experiment that you can try is using those filters. Suppose I promise you this true fact that the light coming out of your cell phone is not just like random light. It's actually filtered such that all the photons coming out are in some angle. You can think about what algorithm you would use with these pieces of plastic to determine what that angle is. It's like you have like millions of copies of the photon all in the same state, and you have this measuring device, and you want to figure out the angle. And in fact, this problem of given either one qubit in an unknown state, or like giving many copies of a qubit in the same state, trying to figure out what that state is. This is a very important problem in quantum computing. It's sometimes called, the quantum people decided to call it quantum state tomography because they wanted to sound fancy. It's like, I would call it quantum state learning or quantum state estimation. It's actually a big component of what I work on in my research. And it's a really important component of quantum algorithms too. You might think it's a little bit funny that like a big component of algorithms would be like trying to figure out like the state of some qubits, because you might think, well, presumably if there's a component of an algorithm like I made the qubits in this state, I should know what state they're in. But not always. It's a little bit like a mystery toggle. Sometimes you write some code and you're like, I don't really know what this does. It does something mysterious. I got to try to figure it out. And one subroutine that we're eventually going to get into, which will be really important for Grover's algorithm and the factoring algorithm, will be the subroutine called rotation estimation or phase estimation, which is really about figuring out like the angle of like a mystery qubit. So that's what we're really going to get into now, this topic of trying to understand like the angle of like a mystery qubit. Okay, so let me tell you like a tiny narrative for this, like just for fun, for this task of distinguishing two qubit states. So these are actually going to be like what are sometimes called hypothesis testing problems. So really put on there like your statistics hat a little bit for this this story. So let's say you're a young child and you're home and your darling, trustworthy mother comes to you and hands you a qubit, as she does, in a quantum state. And I need a character for this who's very trustworthy. So I chose our mom. She has a promise for you. She gives you a quantum state. And she says, this qubit state A is either ket 0 or ket 1. Actually, let me call this state a name. So I'll call that state ket test. Okay? That's another good thing about like the ket notation. You can just write whatever you want. This is a vector named test. It's the state of this qubit that your mom gives to you. You don't know what ket test is, but she does promise you test is either 0 or it's 1, and that's your task to figure out if it's 0 or 1. So I'm going to write it kind of clearly as a question. Yes or no? Is test equal to ket 1? Okay, that's a very easy question, actually. I mean, your mom's a nice person. How could you answer this question? It's easy. It's obvious what you do. You will like do the following. You'll be like, all right, I will just do extract on A in the standard basis, and then if I see 1, I'll output yes. So I'm trying to answer this, and if I see 0, I'll output no. And this is great. What is the probability that the solution, solves the test correctly? It's 100%. It's fantastic. A+. This was easy. Okay. So let's make it a little bit more interesting. Now your darling and trustworthy dad comes to you with a similar test. Okay, so your dad gives you a qubit. Test, and it's either plus or minus, either ket plus or ket minus. Okay, so again, your data is trustworthy, so you believe this. It's either ket plus or ket minus, and wants to know, like, is it ket plus or is it ket minus? So yes or no. Test is plus. This one you can also solve with 100% probability. But of course, you should not do this algorithm. If you do this algorithm, I mean, even you should not do this first step. If you do this first step, you messed up. Because if it's ket plus and you do this, standard extraction, the probability of seeing 0 is half, and probability of seeing 1 is a half. But moreover, if the test vector is ket minus, it's also like 50-50 whether you see 0 or 1. So you see the same thing regardless of whether it's plus or minus. You gain no information about what test is. But of course, you can still solve this with probability 100% using our little subroutine of measuring in a different basis. So the solution is you extract or measure, it doesn't matter, extract in the plus minus basis. Yeah. Effectively, also, you could do a Hadamard and then extract. But we're just going to wrap it up like this. And similarly, you have to kind of convert the output. So if the outcome is plus, remember this returns either plus or minus, then you say yes. Okay. And if the outcome is minus, then you say no. And similarly, this has a 100% chance of being correct. Let me write it all the way out, though, even though it's very obvious, because it'll show you how we'll do the analysis in general. So to think about your success probability with this solution, you have to do cases. So case 1 is that the qubit your dad really gave you was plus. So you first say, okay, maybe it's case 1, maybe it's plus. Then you run your algorithm on assuming it really was plus, and see what's the probability you say yes, because that's the right answer. Now yes is correct answer. So therefore the probability that you're correct is the probability that you see plus on your measuring device. Okay, and I don't know, just to be pedantic, I'll write it out. It's the inner product of the plus vector with the plus vector squared, which is 1 squared, which is 1. Okay, so the probability that you're correct is 1 if the true vector is ket plus. On the other hand, it could be that the true vector is ket minus. Okay, in this case, no would be the correct answer. So in this case, I mean, the probability that you're correct is the probability that you measure it and you see minus, which is also 1. Okay, so again, I mean, your mom and dad, they're so nice. This was, these were easy tests that you can pass with 100% probability. Okay. So now let's make it a little bit more interesting. You leave home, you move to Pittsburgh, or maybe you already lived in Pittsburgh. You go to Carnegie Mellon. You're there in your nice first year or sophomore year. You take this great class called 251. There's a really cool professor, Professor Uda. He's also very trustworthy, but he makes it interesting. It's interesting stuff. So you encounter the trustworthy and interesting Professor Uda. And he gives you a similar, test. So he hands you some qubit in some mystery state, ket test that you don't know. And I should have wrote the word promise here. Test is either ket 0 or it's the vector which is at 60 degrees from horizontal. Okay? So in other words, this qubit that he hands you, it's either this one or maybe it's this one. Where did I mark? Okay, and it's the same kind of question. The question is, let's say yes corresponds to the rotated one. So like yes or no, is test equal to rot 60 degrees 0? Okay, so what are you going to do? Any suggestions? Yeah? Good. You want to rotate the state 90 degrees. So then, if it were 0, it would become 1. And if it were the 60-degree thing, then it would become like over here. And then you want to extract. Yeah, that's what I was thinking. I think you don't even have to rotate, and you'll get like a pretty good algorithm. Let's try this. This is idea 1. Which indeed was the idea I was hoping you would say. Just do the standard thing. So measure in the 0 and 1 basis, the standard basis, which just corresponds to doing extract. Now, actually, what you said will be equally good to what I'm going to say, so it'll be fine if you also want to rotate 90 degrees. But indeed, as you say, so this is like our little algorithm. So first I'm going to measure this. Then it'll either say 0 or 1. So say the readout on our measuring device is 1. Let's say if. Then what should we finally output? We're supposed to output either yes or no as an answer to this question. What should we output? Yeah? Yes. Yeah. In this case, we should not only output yes, but we should like very confidently output yes. We should be really happy about ourselves. And we'll do the analysis, but you can think about why we're so happy. On the other hand, if the readout is 0, output, yeah, here we're a little less happy with ourselves, as you'll see. Because honestly, it could have been, the test was ket 0, in which case we would definitely get the output 0. But it also could have been that, like, test was this 60-degree vector, in which case there's still a 25% chance we would see 0. But let's just output no and see what happens. And this is a pretty good algorithm. I mean, it is. There's a sense in which this is an optimal algorithm. Let's try to analyze it. So now we're going to use this, setup that I said we were going to use here, the case 1 and case 2. So let's do it. So let's do the analysis. So case 1, this vector that Ada handed you. Let's say case 1 is that it's ket 0. Okay, so in this case, the correct answer that you're hoping you output, or that the TAs hope you output, is no. Let's see, what is the probability that that 3 bullet point output or algorithm outputs no? Well, the probability that you're correct, which is the probability that you output no, which is by definition of the algorithm the probability that the readout is 0. Well, what is it? It's 1, yeah, it's 100%. You're measuring ket 0 in the basis of 0, 1, and what's the chance you get 0? It's 1. Okay, great. So if the test vector is truly ket 0, you get the 100% correct answer. Case 2 is like not as awesome, but let's see. So case 2 is that the true state is this 60-degree rotated vector. Okay, and then the correct answer to the test is yes. So let's see the probability that you're correct, which is the probability that you output yes, which is the probability when you output yes if the readout is 1. The probability the readout is 1. Okay, what is it? So here, the true vector is this rotated 60-degree thing, which is this red vector. We're measuring it in this basis of blue and, I don't know if this will show up, orange. So we're kind of asking, if you measure this red vector in the blue-orange basis, what's the chance that you get orange? It's like cosine of this angle squared. This angle is 30 degrees. It's also sine of 60 degrees squared. Okay, so this is cosine of 30 degrees. Oops. Yeah, cosine of 30 degrees squared, which here I guess you need to know your basic triangle is 30, 60, 90. Did I get it wrong?
3/4.
Oh, this is probably you're correct. Wait a minute. Oh yeah, sorry. 3/4. Thank you. Obviously, it's bigger than a half, right? I mean, because this vector is a little bit close. I mean, it's more close to this than it is to this, so it should be above a half. It's 3/4. Thank you. Okay, so this is interesting. I mean, 3/4 is not that great. It's okay. It's like it's a C, right? So it's a funny situation where if this is the test, you nail it. You get like A++. If this is the test, you kind of okay. I mean, you got a C. That's not so bad. And it's a funny kind of, I mean, now we have to really have our statisticians' heads on, or our probabilistic algorithms hat on. This is what's called a one-sided error algorithm. So it's a kind of a randomized algorithm. It's called one-sided error because in one of the two cases you have error, and in one of the two cases you don't have error. So one way to say this one, and I always mix this up, so I'm literally going to copy off my paper. The probability of a false positive is 0. What's a false positive? False positive is like when the true answer is no, but you accidentally say yes. Here, that's 0. That's this case. Here, like the true answer is no. What's the probability you accidentally say yes? It's nothing. If the true answer is no, we got it perfectly right. So this is like no false positives. And then this one is like a false negative. So in this case, the probability of a false negative is 25%, which is not that bad. It's kind of small. Okay, and this is one-sided. Means like one of these two things is 0. It doesn't, I mean, you have two different kinds of one-sided algorithms, like the ones with no false positives and the ones with no false negatives. I also sometimes like to call this particular kind like a yes means yes algorithm, because in this algorithm, if the algorithm outputs yes, then you're like 100% sure the true answer really is yes. Right? Because like suppose the algorithm outputs yes. You say to yourself, wait a minute, could the true answer actually be no, even though my algorithm output yes? No, because if the true answer is no, this algorithm always outputs no. So that's why it's confusing. I think of it like yes means yes. You see a yes, you're like, it's definitely yes. You see your algorithm outputs no, you're like, probably it's no, but there's a 25% chance it's yes. Well, yeah. Uh-huh. Did you have a question?
Why is it not lower than 25? Because like you have all the good weight. Never mind.
Okay. That's cool. One of the weights was W-E-I-G-H-T and one was W-A-I-T. Yeah, this 25%, well, it's a function of this algorithm plus the fact that I chose like 60 degrees here in order to make the numbers come out somewhat pleasantly. Statisticians have different names for this. They have like type 1 error and type 2 error. Did you ever hear that before? But who knows which one is type 1 and which one is type 2? I once heard that like the way to remember it is you remember this like, you know this fairy tale, The Boy Who Cried Wolf? Like first the shepherd kid is bored, so he says like wolf, even though there is no wolf, and then the village comes and they're mad. I think that's a false positive, and you're supposed to remember like that's the first thing that happened in the story, so that's type 1 error. And the other one's type 2 error, but then, yeah, I didn't get never mind. I think this is the best way to like maybe try to think about it.